All right, so happy Monday to all of you. I hope that everybody had a great weekend and that you were really good to your mothers yesterday. I do miss being at school with you, and hopefully I'll be back at it and back with you before too much longer has gone by. But in the meantime, if you have specific questions, please always feel free to email me because I am checking my email daily. For this video, you're going to want your graphing calculator, and we are going to fix some settings on the graphing calculator that will make your life easier as you go through this unit. And in particular, we talk about graphing in Polar. So if you need to, go ahead, pause this while you dig out your graphing calculator. Okay, so I am on page 11 in the Polar packet. And right up at the top of page 11, I'm going to start by making some changes. It says that your calculator should be in polar and, well, should say degree modes. Polar and degree mode. The window usually has to be between 0, and we're going to change the theta maximum value to 360 because we are going to graph in degrees. All right, so we want to graph this very first equation, but again, the very first thing that I'm going to do before I do any graphing is to put my graphing calculator in the correct modes. So to put it in degree mode, I can either go into open up a new graph. Maybe I'll just do that. No, when I add a graph, notice that I am in radians. And if this is you, you want to go to menu. You want to go to choice 9, which is settings. We still want float 12, but we want our angle measure to be in degrees. And notice that now I have changed and I am in degrees. All right, to get into Radian mode, we're going to go and hit the menu button. And when we hit the menu button, we want to hit choice 3, which is graph entry or edit, and then option 5, which is polar. And we want to graph that first equation, which is r equals 4 times sine theta. So 4 times sine theta. The theta you're going to find back behind the pi button. So when I pull up the pi button, it'll pull up all these options. I want theta. And then remember, we want that interval to go from 0 to 360, so I'm going to change that. As far as the step by which to count thetas, I'm going to change that to 30 degrees, but you could change it to 60 degrees. I like 30 here. And I hit enter, and there's my beautiful graph. So r equals 4 times sine theta. If you didn't catch how I said to get in here, well, that's the beauty of having this on video, is you can just stop, rewind, and replay. Notice that the coefficient there on the right-hand side was a 4, and take a look at what the diameter is of our circle. That is no accident or no mistake. I'm going to go ahead and sketch a picture of that. Notice that my circle is centered or has as a line of symmetry the y-axis. So it's a circle. Its diameter is equal to 4. And again, pay attention to that connection there and there. As far as the second part of that question goes, writing this equation in rectangular form, we're going to talk later in the week about converting back and forth between polar and rectangular, and I think I will leave that discussion for a different day. All right, I'm going to go on to the second one that says graph the equation r equals 3 cosine theta. And here's where I want your calculators set to polar and to be using your own calculator every day, so that I don't have to go in and keep changing my theta measure from 0 to 360. I'm going to go hit Control G, which in previous math classes you would have used to enter a second equation. And again, notice that when I try to enter a second equation, what happens is the step is set back. We're set back to 2 pi and in radians. So what I'm going to do is go back to this original equation, and I'm just going to modify the original equation. And I'm just going to keep modifying this over and over again so that I don't have to keep changing the step and changing radians to degrees. So this time I think our equation is 3 times cosine theta. And notice that when I change my function to cosine theta, notice that the equation or the circle is now symmetric about the x-axis. And notice that that coefficient of 3 has changed the diameter of our circle to a 3. All right, so let me go sketch a picture in our notes of what this looks like. So a circle, not only is it a circle, its diameter is 3. And again, we're going to worry about converting that to rectangular form later on this week. Number 3 is asking us to graph a couple of equations. I think I'm going to graph them one at a time so I can draw them one at a time because these equations end up being kind of busy with a lot going on. So again, I'm going to control G so I can go back. I'm going to go right back to my first equation and override it. We want to do 1 plus 2 cosine theta. So notice our graph is still round, but now we have this inner loop coming in into our circle if you want to think about it as such. And again, I'm going to go sketch these one at a time. So it's still kind of circular in shape, but again, it has that little inner loop. And now I'm going to pull up a second graph. So Control G. This time I'm going to have to make some changes. So 1 minus 2 cosine theta. And I want to change this from 0 to 2 pi to 0 to 360. And I'll change the step to 30. So note that that negative in front of the 2 cosine theta just flips the graph right over the y-axis. The y-axis is a perfect axis of symmetry for those two graphs. This is going to be a little tricky to draw. I'll do the best I can. What do you notice about the two graphs? Well, they're symmetric with respect to the y-axis. More importantly, the name for this graph, they're called a limison with an inner loop. And that name you do need to know. And I might go back because my picture is really kind of sloppy. I might go back and just draw one of those on there. It's really hard to get both of them in there. There we go. So that limison with an inner loop, or sometimes we call an inner loop limison. Now messing around with the A values and the B values in these types of graphs or in these types of equations are going to have an effect on the graph. So what we're going to do down at the bottom is go to take a look at how changing these values, or what effect changing these values has on the graph. And I think what I'm going to do, just to keep things easy so that I'm not flipping back and forth between the graph and the calculator, is I'm going to decide upon all my equations first, and then second, go ahead and do all my graphing. So in line 1, it says that the relationship between A and B is such that when I divide A by B, the result is less than 1. So I'm going to make my A value 1 and my B value 2. My A divided by B now is a half. which is indeed less than 1. To make my a divided by b value equal to 1, I'm going to choose 3 for a and 3 for b. You could pick something different if you're so inclined. For my a over b value to be between 1 and 2, I'm going to go right for 1.5. So I'm going to make a 3 and b 2. And then lastly, to make my a divided by b value greater than or equal to 2, I'm going to pick 4 and 2. So my equation for the first one is going to look like r equals 1 plus 2 cosine theta. For my second one is going to be r equals 3 plus 3 cosine theta. For my third example, r equals 3 plus 2 times cosine theta. And for the last example, r equals 4 plus 2 cosine theta. All right, so I'm going to go get down to business and get down to work. I'm going to start right back up at the top again and go graph that equation, 1 plus 2 cosine theta. Oh, and look at that. When you're good, you are good, because I already have that graph right in my calculator. I'm going to go ahead and remove the first graph. Sorry, remove the second. And there's my 1 plus 2 cosine theta. So when my a over b value is less than 1, the result is that lemmason with an inner loop, or an inner loop lemmason. And as far as what it looks like, we already drew a picture. There's another picture. All right, I'm going to go in now and I'm going to change things around a little bit, and I'm going to graph the equation y r equals 3 plus 3 cosine theta. So again, I'm just going to go back and Control G. And this time I want both of those to be 3's, and let's see what effect this has on our graph. Well, now instead of that lemmason with the inner loop, we've got kind of a heart-shaped looking graph, and it's probably not by any accident that this graph is called a cardioid. So I'm going to go ahead and sketch my picture. It looks like it goes right in and touches that polar axis, just so I can be as exact as I can when I draw my graph. So the cardioid is the heart-shaped looking graph. I'm going to go in and switch things up again and make that r equals 3 plus 2 cosine theta. And again, I want to see what effect this has on the graph. Now instead of a heart, this has just a little dimple that doesn't go in all the way to that pole. So I'm going to call this this is called a dimpled lemmason. Perfect. And then the last one we want to go graph is that r equals 4 plus 2 cosine theta. So again, Control G, and I'm just using the same one all over and over and over. And when you first look at this graph, it looks very circular in nature, but when you look a little bit more carefully and a little bit more closely, notice that the left side of my circle really isn't round, but rather it's flattened. So we can't call this a circle because it's not a perfect circle. But the name that we do have for this when we have that flattened side is called a convex limacin. So that is a convex limacin. And again, it's very, very, very close to being circular in nature, but it just has that flattened side. All right, so those are some different types of polar graphs. I'm going to go ahead now and shoot right back up or right up to the top of page 12. And in this instance, we're going to take a look at a slightly different kind of graph. This graph is going to be in the form r equals 2 times cosine of n times theta. So notice that n in the parentheses for some different values of n. So in the first instance, our n value is going to be 2, which will make our graph or our equation r equals 2 times cosine of 2 theta. And again, I'm going to go fill these in going downwards first of all, just to make it less flipping and flopping back and forth between the graph in the chart. This will be 2 times cosine of 3 theta. R equals 2 times cosine of 4 theta, so on and so forth. All right, so I'm going to go back up to the top, and I'm going to go graph r equals 2 times cosine of 2 theta. So again, I'm just always modifying the graph that came before. 2 times cosine of 2 theta. Ooh, isn't that pretty? All right, this is called a rose. And notice that our rose has 4 petals. Notice that the length of each of those petals, 2 units, is the same as the coefficient. So this is a rose with 4 petals. Notice that the petals lie on the x-axis and on the y-axis. All right, I'm going to go switch things up just a little bit here. And I'm going to make that 2 theta a 3 theta, and let's see what happens. So changing 2 theta to 3 theta changed our rose to a 3-petaled rose. So how many petals? 3. And again, notice that one of those petals lies on that polar axis. And that's a little about what, or close to what our picture looks like, as exact as I can draw it. I'm going to go graph r equals 2 cosine of 4 theta. And if I count the petals on this rose now, I find that there are 8 of them, again, each with a length of 2 units. So number of petals is 8. This is going to get tricky. Notice that my first petal does still lie on that polar axis. All right, my next one is r equals 2 times cosine of 5 theta. Anybody want to make a prediction about how many petals you think you're going to see before I hit enter? All right, if your prediction was 5, you are spot on. And again, notice that first petal lies on that polar axis. And then the rest are evenly spaced. And I'm not going to go ahead and actually draw graphs of the remainder of these because the graphs are going to be too busy. So I'm just going to say too busy. But if we had to make a prediction here, when the number of, or when the n value is odd, the number of petals is exactly equal to n. So notice, for instance, that 3 petals when n was 3, 5 petals when n was 5. So if we had to make a prediction here, if n were to be 7, we would end up with 7 petals. Notice that when n is even, so when n was an even number, the number of petals is always twice n. So 2 times n petals if n is even, n petals when n is odd. So again, if we had to predict down here for an even n, we would predict 2n, or 12 petals when n is 6. When n is 8, 2n petals is going to be 16. So that's the rows. All right, there's one last type of graph that I'm going to show you today, and that is the graph of r squared equals 9 times sine of 2 theta. In order to be able to put this into our calculator, we need to go ahead and we need to solve for r. So I'm going to say solve for r by taking the square root of both sides, remembering that when I take the square root of the right side, I have to take both a positive and a negative square root. So I'm actually going to go and graph this in 2 pieces, or in 2 parts. I'm going to graph one of those parts as r equals the positive square root of 9 times sine of 2 theta. One of those pieces is r equals minus the square root of 9 times sine of 2 theta. So let me go back up. I'm going to go back to this r1, which has been a good faithful friend for me. So there's my r equals 9 times the sine of 2 theta. And this time I want r equals minus 9, or sorry, minus the square root of 9 times the sine of theta, 2 theta. Be careful here because the second graph entry is set from 0 to 2 pi. You want to change that from 0 to 360 and change your theta step. And there's my graph that looks kind of like a fan blade. And the name of that graph is called a lemniscate, which you can see in your notes rhymes with Triscuit. So this lesson today, the purpose of this is just to introduce you to all these little shapes and to get you used to and comfortable with graphing polar in the graphing calculator. All right, up at the top of page 13, all I want you to do is pause the video. Once you do that, go ahead and graph each of those equations in your calculator. Start the video back up again and check your answers. And if you have questions about any of these, feel free to let me know. All right, welcome back. So number 3 should have come out to be a convex lemniscate. Number 4 was a circle. Number 5 is a lemniscate. And number 6 should have come out to be a cardioid. Down at the bottom in number 7 through 12, all they want you to do is identify what type of polar graph has been drawn. So in other words, go ahead and name the shape. And again, I'm going to have you go ahead and pause the video and then come back and check your answers. All right, let's see how what you got matches up with what I got. For number 7, I got the 4-petal rose. And notice that when you're going to name a rose, we always specify the number of petals that go along with that. Number 8 was the heart-shaped cardioid. 9 was the inner loop lemniscate. 10 was the lemniscate. Oh, and I forgot my C in there. 11, the 3-petal rose. And number 12, a circle. All right, last one, and then we're going to call it a day in this long video. Number 11 says true or false. The equation of the graph shown is r equals 2 sine theta. Well, I like sine theta because we are centered around or have as an axis of symmetry this guy right here. I don't like that coefficient or that leading coefficient though of 2. A leading coefficient of 2 would have to be a diameter of 2, and the diameter of our circle here is 4. So this is close, but not quite. I'm going to mark that false. If that had said r equals 4 times sine theta, I'd have been all about that. All right, folks, so thank you, thank you, thank you for your time and attention. I'm going to say that homework that is due on Tuesday is going to be page 14. Page 14 is going to be similar to what we did here, and page 17, which is just matching. So it's going to be graph in your calculator and then match it up just so that you've got some practice and experience in graphing these on the graphing calculator. And then tomorrow we'll kind of kick it up a notch and talk about specifics and taking it to the next level. In the meantime, if you need to get in touch with me, please don't hesitate to reach out for help in Teams. You can reach out for help by email. You've got student assistance that's available almost every period of the day. If you're struggling, though, please don't feel like you're in it alone. Make sure that you reach out for help and use the supports that are there in place to help you. All right, take care. I hope to see you soon. Bye.